Welcome to Spring Soil Seminar. It is my pleasure to introduce Daniel Linton. Daniel is a part-time Spatial Laboratory for Soil Informatics here in Iowa State University Department of Agronomy. He is pursuing a master's in soil science with Dr. Bradley Miller as his major professor. Before coming to Iowa State University, he earned his Bachelor's of Science at the University of Wisconsin-Madison, studying environmental science with an emphasis on geographic information systems. At the University of Wisconsin, his research interests saw him moving through many departments, including agricultural engineering, plant pathology, soil science, and remote sensing. Today, he will be presenting preliminary results from his thesis research on the spatial distribution of soil properties on hill slope with perennial vegetation contour strip. Please join me in welcoming Daniel.
Good afternoon. Thanks for taking the time out of your schedules to listen to me yammer on about my research. So today I'll be giving a presentation on soil mapping on a 10-year-old STRIPS site. So first, what are STRIPS? STRIPS is one of the super fancy scientific acronyms. It stands for Science-Based Trials of Row Crops Integrated with Prairie Strips. Iowa is 12.3 million hectares of farmland. That's over 85% of its landmass in agricultural use. One of the major problems we think about with that much of our land in agriculture, or a single thing, is landscape simplification. The strips aim to alleviate that by introducing more complex items to the landscape. And the main goal is to increase to serve multiple ecosystem services. Some of those target ecosystem services, including regulating services. Those would be improving water quality and quantity. They also aim at providing some protection from erosion. If you look at the figures on the left, we've got a classic experiment where at the flumes, at the hills, the toe slope position, we see sediments that have left the normal field and are at the outlet. In the center, there's a 90% row crop system and 10% prairies. That 10% prairie causes significant reduction in sediment loading. And just for comparison, looking at the 100% prairie, there's barely anything leaving that field. The second ecosystem service that is classically spoken about are the provisioning services. These would include wildlife habitat and pollinator habitat. I'll talk a little bit about those later. So I'll hop over into the most interesting part, the supporting services. And those can include nutrient cycling and soil formation. So nutrient cycling is an easier pill to swallow. Perennial vegetation is on the fields for more time of the year, as the row crops are only on the ground for a couple months. Being there the entire time, they're actively cycling nutrients such as nitrate and ammonium, and possibly phosphorus, and granted that one goes a bit slower. And because they're not harvested, the nutrients that are used are kept in a tight loop. Soil formation is a little bit more tricky. So I would argue that the soil underneath the row crop system is mostly moving in a direction that is associated with the agriculture that we're doing on it. The prairie strips provide a secondary environment which will push soil formation at different rates and in different directions. So for a little bit of literature overview. Cox et al. And some others have cited that there's a 2.5 times more natural enemies in fields with prairie strips. They've also cited 3.5 times more pollinators. Zoe et al. And Mitchell et al. have looked at nitrate. So at the center points in our slide, in our diagram, there are wells located there, and also at the toe slope position. They pull samples, and they've pulled samples from water in those two locations, and have determined that there is a 70% reduction in groundwater nitrate. Mitchell goes on to say that there is a nitrate sink down at the toe slope. Finally, Helmers et al. And Zoe et al. Have shown that there is a 96% sediment trapping efficiency, meaning that 76% of the sediments that have left their original location haven't left through the outlet. Associated with that sediment, there is also a reduction in phosphorus, as phosphorus is typically associated with sediment, roughly 98% correlation between those two variables. There's also a reduction in nitrate in runoff, and an overall reduction in water runoff, which can be attributed to infiltration and increased evapotranspiration. So these studies are great. They show the power of the strips. Strips are actually doing something on the landscape. However, they're making their measurements at discrete locations. They're looking at wells that are on the back slope, and they're looking at locations in the toe slope position. Whenever I read papers like these, I always wonder, what about the rest of the field? Not everything is going on in a single spot. Spatial is special. That's something my introduction to GIS professors taught me, and it sticks with me today. Where you sample influences what you see. If I'm at the toe slope, then I'll measure at the toe slope, and I'll measure processes that can occur at the toe slope. If I'm on the back slope, there are processes associated with the back slope. Also, there's a foot slope, and there's a summit. Those locations also have specific processes that are associated with them. My questions follow that line of logic. Do prairie strips alter the spatial distribution of soil properties? And if they do, what are the new spatial patterns created by their presence? That's what I'll be going into today. My hypothesis is quite simple. My hypothesis is that the prairie strips impacts the measured soil properties, and those impacts extend up and down the hill slope. Specifically, the spatial extent of differences above and below the strip will be different, with more elongated effects below and shorter effects above. My reasoning is just following the water. I expect more water to be below the hill slope position, below the prairie strip, and less to be accumulated above. The fields with prairie strips have increased infiltration. They've got more water actually cycling and running through. So I expect other processes such as leaching, such as retarding of carbon breakdown to also be occurring. A quick note on my site description. So I did my study at Neil Smith Wildlife Refuge. The main soil mapping units were Ladoga and the Gar Armstrong Complex. Ladoga was mostly our summits, shoulders, and back slope. In the test plots, we've got the Gar Armstrong Complex. The dominant surface texture was silt loam, and we measured that by a laser diffractometry. And a little bit on strips. This was the oldest site, and it was started in 2007. I took my samples in 2017, making it a 10-year anniversary type study. A little bit more on my sample design. Total N was 147, with samples split between a test 2, and a control plot. I used stratified systematic sampling, which was controlled via planform curvature and flow accumulation. The planform curvature told me where to draw the more vertical lines, and flow accumulation allowed me to transfer the relative location from inside the strip to outside the strip into the control plot. I'm hoping this makes sense, guys. There are no prairie strips on the other plot, so to make a good comparison, I tried matching them hydrologically. There were a suite of soil properties that we were going to measure and model, including organic matter, pH, particle size distribution, water content, extractable phosphorus, and extractable forms of nitrogen. We're only going to focus on organic matter and pH today for simplicity, and that's where I'm up to in my research. So now I'm going to go over the results. The first part is going to talk about direct comparisons using zonal statistic approach. We're going to then see some spatial apparent spatial patterns. The second part, we're going to do some model comparisons using spatial regression approach. Just a small disclaimer, these are not process models. All right. So first, we're going to look at pH. The pH of the control was organic matter, The organic matter of the control was fairly constant. There's a slight hump pattern, and the variability is quite low. The strips plot is not as tightly packed. So the whiskers on our box and whisker plot are tremendously large. There's only, the spatial pattern though is quite similar between the strips and the control plot. If you notice the variability as depicted by the length of the whiskers is similar between the above and the above and the inside and the inside. The below position are both have the lowest amount of variability. So the strips may increase the carbon capacity by a little bit. And we get that just by looking at the means here. There is a significant difference between the above position in the strips and the control plot. However, there is no statistical difference in the inside plots and the below. The variability is something that you really have to note though. Those bars are humongous. pH is slightly different though. So there's a distinct pattern to the pH on the control plot. It increases gradually as you move down the hill. From above to below, there's an increase in alkalinity or reduction in acidity. The strips, plots, or catchments don't share that same pattern. Above the strip is slightly lower than inside the strip, which is significantly higher, and below the strip, which is slightly lower. So there's a hump-shaped pattern associated with pH on the catchment with strips. It goes without saying that these are all statistically significantly higher, so we conclude that that the strips increase the pH of a field that they're applied on. Moving forwards with our results, we're going to look at the modeled comparisons using the spatial regression approach. So the program that we used was Cubist. Cubist does multiple linear regression. It follows a simple structure. There are conditions that have to be met, and then regressions that you apply afterwards. So if the specific condition is met for a pixel, then you apply a regression equation to calculate the value that's at that location. We train the model by feeding it a suite of covariates at varying analysis scales, which I will describe in the following slides. Here's an example of planform curvature. Planform curvature looks to quantify the shape of the hill slope or area location. We start with a digital elevation model and we try to see, is the landform bulging or is it convex? So if the landform bulges towards us, it's a positive landform curvature. And if it is, if it's convex, if it's concave, then it's a negative planform curvature. If it doesn't bulge or sink, then it would have a neutral plan curvature. Just noticed typo. So this is supposed to be profile curvature. Sorry for that. Profile curvature looks to see the upward surface, whether it's concave or convex. Positive would indicate a concave surface, and negative, a convex. The practical version for analysis scale is asking the question, how far do we look when making a measurement? So our stick figure guy on the hill looks out to the pink arrow, and he tries to measure the slope. He'll measure that slope in the light pink vector that's at his feet. If he looks slightly further, using, say, the darker arrow, he'll measure a different slope. So at that location, you can measure two different values for slope. Translating that to a raster grid, we're trying to estimate the value at a point, marked by the X. If we move outwards with a 3x3 window, our analysis scale is now 9 meters. So the pixel size is 3, and we're moving 3 pixels across, making it 9. We can keep going. This is a 5x5 raster cell analysis window. Even further, a 7x7. Now, as we change our analysis scale, the values that we get are going to be different. Imagine that stick figure looking out. He looks 1 pixel in front of him, he'll calculate a value. He looks 2 pixels in front of him, he'll calculate a different value. We took this to the extreme, of course, because we're scientists. The analysis scales that we've measured range from 2 meters, just for our original data, all the way to 702 meters for certain calculations. We started with elevation, which was a bare earth LiDAR, DEM, a digital elevation model, which captures the elevation at a particular location. From there, we transform our data to find other forms of elevation. Topographic position index and relative elevation are 2 other ways to quantify where are you on the landscape compared to your neighbors. The curvatures that I mentioned earlier have other forms, so we've calculated planform, profile, longitudinal, cross-sectional, and minimum curvature. Classically, we calculated slope because it's probably important. And lastly, we have northness, eastness, and area solar radiation. So northness and eastness are just 2 vectors from what you would classically define as aspect. Aspect has a small issue in modeling as it moves from 0 to 360 degrees, where 0 and 360 are the same value. So if you have a number that is 359 and a value that is 1, those should be very close together, but numerically they're split very far apart. So this transformation allows us to measure aspects in its 2 component vectors, skipping that whole issue. I tried using area solar radiation in order to understand what's really going on with that aspect. So you may have heard south-facing slopes are different than north-facing slopes. Well, I expect the reason we would think that is because they're receiving different levels of radiation. We've modeled that radiation and used it as an input. So I have a couple expectations for my model. I expected it to follow the patterns we saw in the zonal statistics earlier. I expect that hump-like pattern to emerge, and I also expect carbon to be slightly higher. Here is one of the models that I've built for the organic matter. I know the overlay is a little bit cluttered, but the values that you see in the circles are the point measurements. The grayscale in the background is our modeled values. So the strips don't really appear to have that big of an impact on this landscape. The models that we generated didn't quite show that kind of separation that we would expect to see, but that's kind of to be expected. We didn't see significant differences across the entire field. When we used the box plots, there were slight differences. Modeled pH was a little bit more exciting. Our models ended up dividing the landscape into several parts. However, we noticed that there is only one case in which the actual location of the samples really played a significant role. So we're going to go on and interpret some of the selected covariates. In this section, we're going to think about how did the algorithms look at the field and how did it best fit those models that we just saw. First, let's look at the organic matter. The means between these two were the same. Statistically, they're similar. So we shouldn't really expect the model to cough up a model that we didn't expect our algorithm to cough up a model that actually separated them the way that we would want to see them separated. So the variability that we do observe on the field can be looked at by looking at the covariates used to actually perform the modeling. In this case, relative elevation at a small analysis scale, 14 meters, was selected. At 14 meters, the algorithm is saying that we're looking not that far away to calculate what's around us. On the other hand, the other rule, which ended up modeling most of our landscape, used a very large analysis scale feature, slope, at 614 meters. 614 meters is way larger than the size of my field. That means the inputs that it was using were smoothed over the landscape. If you're using an analysis scale that looks at if you're using an analysis scale that is quite large, you end up seeing regional trends. At a regional scale, the strips are rather insignificant, I'm sorry. So we expect that organic matter is not going to be picked up by a model like the one that I've constructed. From test plot 1 to test plot 2 and the control plot, the best way to describe or divide the data was by using northness. Then it used relative elevation, which is a relative position on the field, so how high are you compared to your neighbors, and slope, which was generalized across the entire field. If we moved our analysis window down to the catchment, then perhaps we'd see some more differences. The first cut of the data decided that we need to look at the landscape. If we remove that landscape thought, then maybe the next set would be information that has to do with the actual catchment and its environment. So our conclusions, by looking at the model that we used to produce this, is that percent organic matter was best modeled or described using landscape properties. Next, we modeled pH. This one had that special rule. The model that we used to build pH, this is rule number 2 out of 3 and rule number 3 out of 3. Rule number 1 would just make it very difficult to see. Rule number 2 covered most of the cases. It asked, where are you relative to the strips? Are you above the strip, below the strip? If you are above the strip or below the strip, clearly you weren't inside the strip, it modeled you just as it would if you were in the control plots. The second rule, or third rule, second for you guys, decided to group the inside part separately. The means here were statistically significant at alpha 0.05. So each run, each test that you make, if you were measuring pH, you were measuring it above the strip or in the control plot, below the strip or in the control plot below the strip, if you're thinking about it that way. Those can be grouped together. If you were inside a prairie strip, this model would model you differently. And that's pretty interesting. That tells us that the position matters. Not necessarily landscape position, as this was over the entire field that we were modeling and testing. So every time we have a prairie strip, we can expect a pH to have some amount of difference. And our algorithm picks it up not just once, but a couple times. So our conclusions here are that there is a local variable that needs to be taken into consideration when measuring pH on a field with strips, or maybe something similar to them. Of course, no soil scientist would stop just here. We've got future plans to make this a better study. The first thing we'll do are measure and model particle size distribution for the entire field. We're going to try to model water content and create surfaces for that as well. Furthermore, we'll follow with nitrate and ammonium and then phosphorus measurements. We've noticed that, the literature has shown that there is reduced nitrate leaving the field, their nitrate sinks around, and that phosphorus leaving the field has also decreased significantly. If the sediment isn't leaving the field and the phosphorus isn't leaving the field, we would love to see those distributions on there. If there are pools of these nutrients on the field, then perhaps the farmer that has strips doesn't have to apply as much material, as much fertilizer. And of course, why would I stop there? We're spatial scientists. Why stop at the surface? Soil is a 3D environment. We took some cores across the entire field, 16 of them, and measured so far thermal properties to see how that incoming radiation will interact across the field. We'll also go forward and measure the classic nitrate and phosphorus and try to continue and make more interesting models with this. I'd like to acknowledge some of the guys that helped me get my data where it is. Jonas, Josh, and Z, and Stephen Potter, one of Marshall McDaniel's undergraduate students, helped me do sampling on 2 outings. I'd love to thank Dr. Bradley Miller. He allowed me to design my experiment and pretty much let me dabble in nearly anything I was thinking, which is really great. And also reined me in. I'd like to thank Mustafa and Dr. Thompson's lab in general for letting me use their resources, the Muffle Furnace for organic matter, and teaching me, letting me use the stuff for pH. Dr. Lee Burris allowed me to use some of his lab for some of the physical property measurements that we're making. A small extra mention for Dr. Horton, sorry not on the slide, for the thermal properties and getting me thinking about that in his soil physics class. I'd also love to thank the STRIPS team at Iowa State University. I've hopped onto their project and they've been very open with helping me answer all the questions that I've had. And of course, the Neil Smith Wildlife Refuge for letting me poke so many holes in their ground. Thank you. Questions, feedback? Yes.
Very good presentation, Daniel. I really liked it. The way that you present your slides were very. I like the image that you used. So my question goes, going a little bit into your project is, I don't know if you mentioned or not, like at which depth did you do the soil sampling, and how? So that's my first question. What was the depth of your soil sampling? Did it vary different depths, or did you have a fixed depth?
Yeah, so I did have a fixed depth. I measured the surface soil at the top 10 centimeters. So the field is in a corn-soy rotation and is no-till. So when I said that the surface soil may be carbon saturated, the field is a no-till, so you expect carbon accumulation at the surface. After 10 years, it would probably slow down, but the strips did show that they increase the actual capacity just by a little bit. Not enough to be significant, but enough to see.
Okay, a follow-up question. Why did you guys decide to do it at that depth? Because it's kind of shallow and mostly you will have some residues like interfering with your something.
Yeah, so if I could do it again, I would take all the samples in the world and probably down to 2 meters. So my original plan was to build a completely 3D map, but it becomes a little bit impractical for all the tests that I want to do. So we aim to focus on the spatial aspects and not the actual differences, the differences that other studies have done. So you can measure at a single point very well, you can measure through time very well, or you can measure over space. And we were focusing on the spatial part. Thanks. That's excellent consideration, though. If I get some more funding, I would love to expand on that. Yes?
So, typically, we have done prairie versus cultivated comparisons, like taking samples across the fence line on native prairies and cultivated fields. And we find 40-50% loss of soil organic carbon, or lower soil organic carbon levels in the surface soil of the cultivated field. So your prairie strips have been in for just 10 years, and you didn't really find much difference in soil organic carbon levels. So how long is it going to take, or are we ever going to get back to where we used to be?
Right. So I did mention that there were different soil-forming environments on this field. So in the prairie strips, you have native vegetation. It's very diverse. It's got deep roots. And in the corn-soy cultivated row crop area, it's typical corn-soy. So I do expect to see some differences, of course, right? You expect carbon to be exuded down with those longer roots, but we're only sampling in the top 10 centimeters. I think that soil is carbon saturated. Now, because it's a no-till, the place where you'd expect carbon to accumulate is now moved up to the surface. So I don't really think I'll see the biggest differences there. That's why we went back and took those 16 cores. If you come to my dissertation in December, we will have all of that data available for you guys to see. And visually, it's striking. You can't tell if this soil came from the summit. You can't tell if it came from the foot slope. The soil sample may have come right from the back slope or from that paleosol, Gar-Armstrong complex. It's very difficult to tell. So the differences that you would expect to see, the striking differences, occur probably deeper down with that 10 years time. Thank you. Yes?
The story is a little more complicated in that in 2007, the site was converted from grassland, CRP set aside, to corn and soybean and to strips.
Mm.
So prior to 2007, there wasn't any corn and soybean. So it's not as if the strips were imposed on corn and soybean land. It's that this whole piece of ground was converted from a poor quality grassland to a mixture of crops and prairie or just crops. So rather than a century of row crop production or some semblance of that, we actually have two parallel things going on. Row crops and strips of prairie on land that had been in low quality grassland.
Hmm. So we're really seeing the decay of grassland on the row crops area?
So you're seeing, in my humble opinion as a non-soil scientist, you're seeing land that was largely protected from erosion
Hmm.
up until 10 years ago. And then a single tillage event converted sod to ground that was used for row crops for reconstructed prairie. Right? So maybe there's been a divergence, or maybe, as you mentioned, the ground is carbon saturated. The organic matter levels you have are 5.5 to 6%.
And some of them are higher too, yeah.
Relatively well cared for, and then over a 10-year period, the row crop land was maintained in no-till, and prairie strips were maintained without any further soil disturbance.
Hmm.
So it's a little bit different than putting prairie strips on ground that had a historic pattern of crop production and seeing what the change was.
Yeah, thank you.
Okay.
Yes, Dr. Thompson?
So in that context, Dr. Laird's question might be rephrased to be, after 10 years under no-till, there hasn't been enough erosion or loss of carbon to show a difference, rather than a comparison of an accumulation of carbon.
Mm.
How long will it take for carbon to be lost under no-till for us to be able to measure the loss? That might be a rephrasing of this question.
Or maybe it won't be lost.
Under no-till. But you did find a change in pH.
Mm-hmm.
So one question I have for you then is, do you have any ideas of what the mechanism would be for that difference in pH between the two cropping systems? Or in effect, two cropping systems. I mean, it's one cropping system, but you have two different kinds of crops.
Yeah, so I haven't really given that too much thought. It may have something to do with perennial vegetation being around and you're not losing nitrate to leaching all the time, which would increase the acidity, decrease the pH. That's a possibility, but again, I haven't really looked into it myself.
I don't know what the management regime is there, but you might look into differences in nitrogen fertilization.
I think they're all managed the same. The only
So
difference would
adding
be...
nitrogen to the prairie strips in the same way.
No,
adding nitrogen
sorry.
to the corn and soybean?
I missed that. I misspoke that. Sorry. So the cultivated part of the field is receiving the same treatment across all of the catchments.
I have one other question to ask him.
Yes.
I'm not sure I understood what you were saying about the impact of northing, which is still an unusual word for me.
Yeah, it's unusual to me too.
But it seemed like you said that, and I wasn't sure whether this referred to the organic matter or the pH, but the impact of the northing variable was greater than the impact of other soil properties. Is that what you meant?
Not quite. So,
If you could go back to the slide that you were referring to, and could you explain maybe a little bit more what northing means and which variable or which measurement related to northing?
okay, so northing is a component of aspect.
I'm sorry, I really couldn't interpret this slide at all, but if you could show the map, where
Okay.
you show the northing coordinates, that might help me understand better what you, yeah, like that.
So, well, my north arrow has disappeared. Sorry. But yeah, north is upwards.
Yeah.
Oh, it's upwards. Sorry, the actual arrow
Okay, I
has
was thinking
disappeared.
that north was going.
No, sorry.
Yeah, oh, okay, that helps me.
Yeah. Some of those graphics are actually gone. Yeah. So when we refer to northing is part of aspect. So aspect asks you which direction is the surface facing? Is it facing northern? Is it facing south? Is it facing west? Is it facing east? The way that it's normally measured numerically is from 0 to 360. Measuring on 0 to 360 makes a small complication for calculations, as 0 is 360. So a high value is the lowest value. So we separated those two. So the degree of how north-facing you were was a useful way to divide the data.
So it was related to the aspect.
Yes.
Of the.
Yes.
Okay, that helps a lot. Thank you.
Exclamation points. That's way exciting. Yeah, Dr. Horton?
I just wanted to ask a little bit about the surface topography, the microtopography. And you spoke about it, but I didn't quite catch exactly how you computed it or what you did with it. But it seems to me that it's important in a hydrologic sense, whether it's mounded, what you were calling the convex microtopography or concave, whether it's going to tend to trap some water or water is going to run away from it. And for me, I think the way you talked about your digital elevation values every 2 meter, that was
So for the base data, we use 2 meter elevation raster. So the size of the pixel was 2 meters by 2 meters. Once you do an analysis on that, you need a window. So the windows start at 3 by 3 and then move up every odd number. So 3 by 3, 5 by 5, 7 by 7. Yes?
I don't know anything about your algorithm. I know less than nothing, but just in my mind, just thinking about trying to do some calculations of the microtopography. If you can have an equation, a model, polynomial or whatever, that could be descriptive on a local sense of the data that you have, and you take the second derivative of it, it will tell you where you have peaks and valleys in there, and where you sample, whether you're sampling on a peak or a valley, might be something of interest for capturing on a local scale some hydrologic feature.
That sounds brilliant. Thank you. Thank you very much. Yeah, I'll definitely try that. Yes.
I believe you have a paleosol in there. Did you go
Yeah.
back to the soil map?
Ooh, it's my least favorite part of this presentation. Let's go back. Da-da-da.
Yeah, there we go.
Okay.
So the Gar-Armstrong complex, that's part of the paleosol region?
Yes.
Okay, the paleosols in Iowa are generally, let's just say they're infamous for having higher clay content, and slower hydraulic conductivity, permeability, for perching water tables. So how does that influence the hydrology of your of your control versus your strip components?
Yeah, so the texture we measured at the surface were all silt loam. The clay content was pretty constant, to be honest.
But that was just 10 centimeters, right?
Yeah, top 10 centimeters. So, of course, we went back later and took deeper cores. And we will be testing, we're going to try to build a three-dimensional map to suss out some of the real topographical complexities of this landscape. Now, the Gara-Armstrong complex does have a small loess cap on top of it, as described in the official soil description. So we're going to try to, put that into context on our field as well. Most of the Ladoga it's just the parent material is loess. In the Gara-Armstrong, so when we were taking our deeper cores, in this section of the field and a little bit down here, we did see some clasts on the surface and obvious or clear indications for redox. So there are differences on this field that have pre-existed or that were there long before the strips came along and before that conversion was really made. So yeah, we'll try to accommodate that new information. Yeah.
So, well, earlier you said that you tried to get similar hydrologic conditions.
Right. Where are
Did you
samples?
factor that paleosol into that assessment?
So the hydrologic conditions we were considering were flow accumulation, so water moving across the surface.
So surface topography only, not subsurface.
Right. And most of our samples, the majority of our samples were on the Ladoga. So comparing the control back to the test 2 and test 1, we're comparing less for less at this rate. So we do expect, water table is going to vary. We expect that to happen. But we don't have a way immediately, as of today, to show how that really has an impact. Our deeper cores should shed some light.
Something to watch for as you move forward in your research, because that could have a big influence on the subsurface hydrology.
For sure. Yes?
The values of the organic matter were concentrations of organic matter or stocks?
That was a percent. So it's...
The concentration.
Yeah, it was easier... it's easier to model an index value.
Yeah, so I suggest if it's possible to calculate the stocks.
The raw values, yeah.
The stocks
Uh-huh.
for the 10 centimeters or whatever depth you use.
Yes.
You may find some differences.
Sure.
If the bulk density is there.
Yeah. That's in the works.
Do we have any other questions for our speaker? All right, let's thank Daniel.